Hello students, in this video I'm reviewing the concepts of moment generating function and probability generating function. So we start with the moment generating function, which has this definition. Okay, so this is the definition. The moment generating function of a given random variable, here denoted big X, is this: the expected value of e to the tx. Now, what is t? Is simply the argument of the function. So you see it's a function of one argument, t, and we have t here in the definition. Expected value of e to the tx. Now, a few things to note. So the moment generating function characterizes a distribution in the sense that it uniquely identifies a distribution. If you have two random variables that have the same moment generating function, then you know they have the same distribution. Exactly like if you have two random variables and you know they have the same cumulative distribution function, then you know those two random variables have the same probability distribution. And that's not necessarily a trivial point. If I give you two random variables and I tell you they have the same expected value, of course, that doesn't tell you that much, right? They still can have different distributions. But if you know the random variables have the same MGF, you know they have the same distribution. And the MGF is often used in proofs. So you can see it as an additional tool to derive some results. Now, another comment to make is that sometimes it doesn't exist. Okay, so careful with that. This is definition, but it assumes that you can compute this thing, meaning this is an expected value. So for a discrete random variable, it's going to be a sum. For a continuous random variable, you compute this as an integral. Now, a sum and an integral might diverge, in which case, if when you compute this, you get to something that diverges, then the MGF does not exist. Okay, so here, this is the definition, but provided that this expectation exists, at least for some t, okay, for some t in some interval centered at 0, okay, meaning if you have 0 here, if this is computable, okay, it's a convergent quantity, for t between minus b and b, then that's how you define the moment generating function. Otherwise, it's just undefined, or you might say it doesn't exist. Okay, now a bit of mathematics here. Using the property that e to the x is just by definition this infinite sum of x to the power k divided by k factorial, we can write the moment generating function, if it exists, in the following way. Expected value of the infinite sum. So here, because we have e to the tx, we can write this as infinite sum of tx to the k, okay, where k, and the summation runs from 0 to infinity here. Okay, but then see, expected value of a sum, if it exists, you can write it as the sum of the expected values. Okay, so you put the expected value inside of the summation, so you get the what's over here. Expected value of now x to the k, and then this is seen as a constant, so you can put it outside the expected value, t to the k divided by k factorial. Now, this is the compact notation. You can write it here in the long form for k equals 0. So the first term here, you see x to the 0, that's 1, and t to the 0, that's 1 as well. So you have 1 here. Okay. Remember, 0 factorial is by convention defined as 1. Okay, so the first term is 1, then you have expected value of x times t, expected value of x squared times t squared divided 2 factorial, blah, blah, blah. Now, it's useful to write it explicitly like that, because then you can hopefully see the very useful property stated here, that you can always find any moment of a random variable using the moment generating function, and hence the name moment generating function. What I mean is this: the kth moment, maybe here we could have written that we mean, k an integer, okay, 1, 2, 3, blah, blah, blah. So any moment of x, what you do is you differentiate the moment generating function k times, and then you evaluate it at 0, and that's it. You get your moment. Now, why is that? hopefully you can see it by looking at this equation. Differentiate, but I think it's easier if we give a specific example, right? Let's find expected value of x to the 3. Now, so here we would differentiate this whole thing 3 times. Now, this you differentiate once, it disappears. This you differentiate once, you're gonna get ex. You differentiate again, it's gonna disappear. This thing again, same thing. You differentiate it 3 times, it disappears, right? So those 3 terms disappear. Now, let's look at this thing. Differentiate it. So view this as a constant. So of course you differentiate with respect to t. So then differentiate t to the 3 one time, you get of course 3t2. Then differentiate again, you get 6t. And then differentiate again, you get 6, right? Now 6, you can also write it as 3 factorial. So what remains is then 6 times this thing, but the 3 factorial cancels the 3 factorial, and you get indeed what you want, which is expected value of x to the 3. Now, of course, you have all those terms. Okay, now those, when you differentiate them 3 times, they're gonna be some t to the power of something remaining. But this is where this bit kicks in. Those terms that have some t remaining, you evaluate t equals 0. So those terms also disappear, and really what remains is this part. Okay, and this is true. Now I'll just show an example with t equals I call this t k equals 3 here. We differentiate 3 times, but it works for any k. Okay, and so this is really quite nice. With the moment generating function, you can get all the moments like magic. Okay, to fix ideas, let's have a relatively simple example here. Now, you have this character, Josephine, and she's apparently using a dating app. Now, you know, I don't know how you know this, but you know that the number of likes she's going to get in any given week is as the following moment generating function. So big X here as the following moment generating function. And here lambda, we just denote, we just say that it's just a parameter, okay? How many likes can Josephine expect? Okay, keyword here, expect next week. Now here, we're simply asking you for expected value of X. Now, you might recognize straight away, because you've been very studious in previous courses, that this is the moment generating function of a Poisson with parameter lambda, in which case you know that the expected value is lambda. Okay, that's a fine way to resolve this question. And sorry if I spoil it for you by telling you the answer straight away, which is expected value of X is lambda. But if you've forgotten that this is the MGF of a Poisson, you can just apply the property we've seen here. You find the first moment, which is the expected values, by differentiating this one time and evaluating it at t equals 0. So let's do that. I mean, you should do it yourself, but now I show the solution. Differentiate the MGF one time. So you take the derivative of this expression over there with respect to t, of course. Now, derivative of e to the power of whatever is always going to be e to the power of whatever unchanged, but then times the derivative of whatever is inside whatever is e to the power of whatever. I mean, you take the derivative of this bit now with respect to t. Now what happens? Derivative of a constant disappears, so what is left really is the derivative of this, but the derivative of this is itself, right? Because the derivative of e to the t is just e to the t, and the constant in front doesn't go away. Okay, easy enough. You get this is the derivative you wanted, and now remember you evaluated at t equals 0, and pretty much everything disappears, right? If this is 0, you get 1 minus 1, so you get e to the 0. This becomes 1. Lambda is here, and then same thing. This one, e to the 0, is of course 1. So as expected, we get lambda. So Josephine can expect lambda likes next week. lambda, of course, is generic. We don't know how it is, but we hope for Josephine that it's a high number, so she gets lots of likes. Another property that is quite useful regarding the MGF is that the MGF of a sum of independent random variables has an easy expression, which is what is explained here. So let's review that. Imagine you have x1, x2, x3, blah, 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 up to xn. They are independent random variables. So the fact they're independent is important here. Consider their sum, and this is something we're going to see very often in this course. We're going to be very interested in the sum of random variables. So the sum S is x1 plus x2, blah, blah, blah. Of course, S itself is a random variable. So you might be interested to find the MGF of this S. Now, what is it? Well, by definition, it's going to be MS. Okay, I'm trying to use the same colors. So I'm going to keep T to be blue, and I'm going to have S a different color, maybe gray. Okay, so we have MST by definition is the expected value of e to the T S. Of course, S is just the sum. But now realize that e to the sum of something, you can write it as e to the first term times e to the second term times e to the third term, blah, blah, blah. So you write it like that. And now, if you recall, for independent random variables, the expected value of a product is the product of the expected values, okay? So that simplifies our life, meaning here you can write this line because of independence as expected value of the first random variable times expected value of the second times blah, blah, blah. Okay, and now that you're here, hopefully you recognize that this is simply the MGF of x1. And here you will have the MGF of x2 and etc. Well, yes, look at this. Expected value of e to the tx1. Yes, indeed, it matches the general definition of having expected value of et random variable x. Okay, so that's a punchline. You get simply the multiplication of all the individual MGFs for all those x's. Now, just a comment, in case it's not clear, they all have the same argument, okay? This is the t that's here is the same argument, mx1 of the same t here, and then t here. Okay, I think that's all I have to say about this. Now, just note that, of course, if those x's are identically distributed, meaning they all have the same distribution, then this simplifies further because you're just multiplying mxt times mxt times mxt times mxt n times. In the end, you get mxt to the power n. Okay, so this mst, there's just one argument here, little t, is just mxt to the n. Now, as a note, this is often useful to deduce the distribution of this sum S, which is often of interest. In the case where you compute this thing, so let's imagine you know what mxt is, and then you compute ms like that. If you recognize this as being the MGF of a known distribution, then you can conclude that S as that known distribution. Obviously, that doesn't always work, but sometimes it's a trick that you can do to very quickly find the distribution of S. And to illustrate this, we have, of course, an example involving our new friend, Josephine. So again, assume that Josephine, her number of likes in any given week as the MGF as seen previously. Okay, this expression over here. Now, as we mentioned, this is in fact the MGF of the well-known Poisson lambda distribution, where again, this lambda is simply a parameter. Now, if we make the following assumption, the number of likes per week are independent. So in different weeks, the number of likes she gets, all those numbers are independent. But they always have the same mean lambda, and they always distributed as a Poisson. What is the distribution of the number of likes in a period of n weeks? Now, you see, this exactly matches the situation we've just presented, meaning here we have that we can call S the number of likes she's going to get in n weeks. And obviously this would just be the sum x1, the number of likes she gets in the first week, plus x2, the sum, the likes she gets in the second week, and blah, 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 up to the nth week. And here, indeed, we assume that all those x's are independent as stated in the question. Now, what is the distribution of S? Well, let's try to apply the method we have just seen. Meaning, we derive the MGF of S as function of the MGF of X. Again, X being the number of likes in 1 week. We assume every week has the same distribution for the number of likes, so we can indeed apply this simplified formula. Now you see here it's easy because you see e to the lambda blah 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 to the power n. You can just put the n in front over there, and then you obtain that you have your e to the lambda n blah blah blah. But look at this. This exactly matches the MGF of a Poisson. It's just that we have a new updated parameter. It's no longer lambda, it's lambda n. Okay, but because it has exactly the form of the MGF of a Poisson, you know it's a Poisson. Okay, it's the only possibility. So here we simply conclude S is a Poisson with new parameter lambda times n, which might be a result you've seen before. The sum of independent Poisson is again a Poisson with updated parameter, lambda being the sum of all the individual parameters. Okay, but now here, the parameter of x1 is lambda, the parameter of x2 is lambda, blah, blah, blah. So you sum n times lambda, of course, you're going to get lambda times n. Okay, hopefully that's relatively clear. And we move on to the next concept, which is the probability generating function. So now this is another function we can use to characterize a random variable and to derive some theoretical results. Now careful, this one, the probability generating function, is defined only for x that are discrete, but furthermore, they are defined on the integers starting from 0. Okay, so here, maybe I should have said that. The MGF is very general in the sense that I'm not assuming x is continuous or discrete or anything here. Okay, it always has this definition. Now, for the PGF, the definition makes sense or is applicable only if x has support the non-negative integers. So 0, 1, 2, 3, blah, blah, blah. Okay, in which case we define this PGF, probability generating function, as follows. We denoted just big G. You might see it denoted in other manners elsewhere, but big G is a relatively standard notation for the PGF. So it's a function of one argument again. Here, just to differentiate it from the MGF, we're going to call this argument R, but I could have called it T again. It's expected value of R to the X. Okay, but you see it's a bit different than the MGF. MGF, we had expected value of e to the tx. Now the argument was to the power, well, e to the power of the argument t. Well, here we have it as the how do you call the base of the power. So it's expected value of the argument to the random variable x. Now recall x is discrete, so you can write this expected value as follows. Take each term at a time, right? Imagine well, it's the first one, x equals 0, you're gonna get r to the 0, that's 1, times probability that x is 0, so you get that, and then etc. When x is 1, you get r to the 1, which is here, and then times the probability that x is 1, and etc. Because well, remember, this is implicitly using the formula that to find the expected value of a function of a random variable, you can just write that this is, call this a function of the random variable, call this generically g of little g of x. Okay, you can still write this as the sum of g of x times probability that x takes whatever value here, all the k's. Okay. Okay, that should be clear enough, I think. And then, of course, you can write this in more compact form over there, if you prefer. Okay, where you have the infinite sum of r to the k times the probability that the random variable takes the specific value k. Okay, and this is defined, of course, just careful. This again is a sum. It might diverge for some values of R. So we say, no, this is well defined for all the values of R, such that this sum is finite, okay, or converges. We have a sort of a neat property as well with the PMF. This property gives us the probabilities of the random variable X. And this again explains why the name is probability generating function. From this big GX, by differentiating a few times, you can always get the masses, so the PMF of X at any value K here. Okay, and the property is stated here. Right, that X is specifically K. You differentiate the PGF K times. You evaluate it at the argument R equals 0. You divide here by K factorial, and that's it. That gives you the probability mass function at K. This is very analogous to the property we saw for the MGF that gave us the moments. Okay, but here we obtain the probabilities. We can do an example just to make sure. Let's find px equal 2. Okay, so here we would need to differentiate this thing twice. Now again, same logic as with the MGF. You differentiate this once, this disappears, then you differentiate this twice, this disappear. This one is not going to disappear. You're going to differentiate twice, you're going to get P of 2 times, okay, you differentiate this twice. Well, one time you're going to get 2R, then again, you're going to get, you differentiate again, you get 2, okay? But then because you divide by K factorial, in this case, 2 factorial, you get to your P2, okay? And then again, those terms, when you differentiate them twice in this example, the R, you're still going to get the R to the power of something, but because you evaluated at R equals 0, those terms disappear. Okay, so really the only thing that remains is the P2, which is exactly what you want. Okay, if you're not convinced by this, give yourself another example. Okay, find P, apply this formula with K equals 3, differentiate everything 3 times, you're going to see that all that will remain is P3. What else is there to say about the PGF? Some properties here. Now, there are some neat relationship between the PGF and the MGF stated here. So, assuming those quantities exist, okay, for some t here, you can write mx t. Basically, you can start from the MGF and get to the PGF. That's relatively simple to do. This is just this part is just by definition. Then e to the tx, why not write it as e to the t to the power x? That works. But then why do we do that? Well, we can recognize that here we have e, well, expected value of a constant to the power x. But that exactly fits the definition of the PGF, which is the expected value of a constant to the x. Okay, now the constant here denoted generically r for us is this whole thing etx. Okay, so make yourself make sure you agree that this is just the PGF evaluated at the argument e to the t. So this is going from MGF to PGF. You can do the opposite. You can go from PGF to MGF. How do you do that? Again, just relatively simple manipulations. Start with the definition. Gx evaluated at the argument r is this by definition. Now, cleverly rewrite r to be this thing, e to the power of ln r. Well, I guess that works. E and ln are opposite operations, so e to the ln of r is just r. Hopefully you see that. And then what happens? Well, you have this, you can view it as a constant. It is to the power of x, but then property of powers, you can just put the x in front of the ln r. And then I think you have what you want, because you see, you have x to the value of e to the x times a constant. Well, that exactly fits the general form of the MGF. expected value of e to the x times a constant. Yes, indeed, it fits the general form. Expected value of e to the x times a constant, generically called here t, but here we have, it's like saying that t is ln r, meaning we have the MGF evaluated at the argument ln r. Okay, so you can go from one to the other. We have the other property here. What is the PGF of a sum of independent random variables? Analogous to the case of the MGF, is just the product of the individual PGFs. Well, indeed, write the PGF of S. It is just, by definition, expected value of R to the sum. But now again, you can write R to the sum as Rx1 times Rx2 times R to the power x3 times R, blah, blah, blah. And then you have the expected value of a product of random variables. You can write this as the product of the expected values. Okay, obviously, this one is expected value of R to the x1, blah, 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 which is by definition of the PGF. Okay, one last property that can be quite handy. You can actually get the first moment of the random variable x by this formula. Now, careful, you differentiate the PGF one time, but then you evaluate the argument r at 1, not at 0. Okay, so careful with that. You evaluate the argument at r equals 1. Exercise for you. Try to show the above. Okay, that's a property I give without proof. Can you show it? Start with the definition, derivate, evaluate at r equals 1. It's relatively easy to show the following property. Try to do it yourself, but if you don't have the time or you prefer me to explain, I can explain in the solution, which is here. It's just 3 easy steps. This is the definition of gx. Okay, by definition, this would be the infinite sum, r to the k, blah, blah, blah. The k goes from 0 to infinity. Now, differentiate it once with respect to the argument r. What do you obtain? Well, px doesn't have any r in there, so px is left there by itself. This, you differentiate it just one time. Obviously, you know that the k is going to go in front. And then you're gonna be left with r to the k minus 1. But now realize the following. If you evaluate this whole thing at the specific argument r equals 1, well, this whole thing disappears because 1 to the power of whatever is 1. Okay, so this evaluated at r equals 1 is just 1. And then you're left with this. But this is just the expected value of x, right, by definition. Pretty easy, I think. Okay, I'm going to stop the video here. Thanks so much for listening. I'll make separate videos to cover all those other subsections. So bye-bye for now.